In order to understand how Smith College is affecting the Mill River as we try to manage the sediment that builds up in Paradise Pond, one of the things we've been doing is assessing the impact or potential impact on freshwater mussels. We have been measuring mussels at two different sites, one in the Manhan River and another site in the Mill River. So here is Paradise Pond. So this sampling site is the mussel sampling site is downstream of the pond. Unfortunately, there aren't any good mussel sites upstream of the pond, so we're using the Manhan River as a control to compare, like, what are just the background things that might be happening in the environment due to weather or predators or something else. So what we do at these sites is we do a systematic sampling design using 50 by 50 centimeter quadrats. We identify the mussels and we measure their shell length. So here you can see an example of measuring the shell length. In this study, we're using what's called a BACI design, which stands for Before-After Control Impact. So in this example, we're looking at the before sample is in the fall of 2015, and this is before we redistributed any sediment in Paradise Pond. Then the after sample is in the fall of 2016, after the sediment was redistributed. As I mentioned before, the control site is the Manhan River and the impact site is the Mill River. These two photos here, the one on the left shows a compilation of photographs taken by a drone showing the buildup of a lot of the sediment. You can see there's some greenery growing on the buildup of sediment in the pond. And then on the right-hand side, this is when the water was drawn down, and you can see that we redistributed a bunch of sediment and flattened it out. When the pond was filled back up, you couldn't see. Now it's basically all water. And during this redistribution, a lot of sediment did travel downstream, so we want to see if this had any effect on the mussels. So you can see here that we have two time points. So year is one factor that we need to take into account. And the other thing is we've got two locations, two sites. So what kind of test are we going to need to understand what's going on with these data? Well, the measurement variable, the length of the mussel is a measurement variable. So we know that our dependent variable that we're interested in is a measurement variable. And we also have at least one nominal variable, year, that we have two groups, 2015 and 2016. And then we also have another categorical nominal variable in location. So we have one measurement variable and two nominal variables, right? So we have two different categories that we're interested in, location and year, and one measurement variable, the length of the mussel. So what we need is a two-way ANOVA. As usual, I highly recommend going to the Handbook of Biological Statistics, which is biostathandbook.com, and finding the information on a two-way ANOVA. So we scroll down, we look for tests for one measurement variable. There's one-way ANOVA. Here's two-way ANOVA. And reading this to make sure you understand what a two-way ANOVA is, what it does, when to use it, what is the null hypothesis, how the test works, some further examples, how to graph it, some similar tests, etc. One thing you'll note is that for most of the tests we've used in this class, the Handbook of Biological Statistics has supplied an Excel spreadsheet template, but there isn't one for this test, unfortunately. So what we're going to do is we're going to use another website to do the actual test called Vassar Stats. So it's just vassarstats.net. And we're going to go to ANOVA, and we're going to select Two-Way Factorial ANOVA for independent samples. So you should read all of the instructions to make sure you understand how to perform this test. this example has, it's what's called a 2x2 factorial design. So we have two factors, year and location, and then within each of those there's actually two different categories. So we call those levels within the factor. So there's two levels of year, 2015 and 2016, and there's two levels of location, Manhan and Mill River. So what we need is a 2-row, 2-column setup. We're going to click on Setup. Now, the difference between an unweighted and unweighted ANOVA goes a little beyond what I expect you to really understand for this class, but just note that each of these what you're going to put in each of these cells is the data for a combination of those two factors. So each of these cells will have a set of data in it. If the number of items in each of these cells is equal, so if you had an n of 10 for each of them, and they're all exactly 10, it's called you have what's called a balanced design. In that case, it's usually best to just use the regular weighted ANOVA. If you have an unbalanced design, that means you have a different n in these different cells, and you'd probably use an unweighted design. So let's see what we have here for the muscle length data. So the muscle length data, we've got the Mill River in 2015 and 2016, and we've got the Manhan River in 2015 and 2016. I've just set it up so that I have the data kind of arranged like how we're going to put it into Vassar Stats. I think I'll make this a little smaller so we can see both of them at the same time. So what I'm going to do is I'm going to have column 1 be 2015, so everything in this column is 2015. Column 2 is 2016, so everything in this column is 2016. Row 1 is the Mill River, so everything in this row will be the Mill River. And row 2 is the Manhan River, so everything in this row is the Manhan River. So in this column, I need the data for 2015 for the Mill River. So I'm going to take these data. I'm just going to take all the data for 2015 for the Mill River. I'm going to copy it, and I'm going to paste it. Notice that in most cases, there's an extra blank spot here. It'll treat it as a 0, and it's not actually a 0, so you want to make sure there's no extra blank spot at the bottom. You just make sure to delete it and make sure there's no extra space at the bottom, and that your cursor ends at the end of your data. We're going to put in the values for 2016 for the Mill River. Again, get rid of that bottom thing. I'm going to put in the values for 2015 for the Manhan River and the values for 2016 for the Manhan River. So remember, each of these values is, these are the dependent variable, right? Each value here is the length of an individual muscle measured in millimeters. And then we've got 2 years and 2 locations. And as I said before, if your n is the same for all the cells, then you have a balanced design. But if it's not the same for all the cells, you have an unbalanced design. You can see here that we don't have an equal number. There's only, I think it's like 11 measured muscles in the Manhan River, whereas there's a lot more in the Mill River in 2015. So we do not have a balanced design. So I'm going to use an unweighted ANOVA, two-way ANOVA. Okay. Now I'm just going to click Calculate, and first what you'll see is in each of these cells, and you can expand them because you can see when it's like this number kind of goes across 2 rows. So I'm just going to expand these, make sure we can see the full data there. So these values in each cell represent these values up here. So item number 1, this item, is the n, that's the number. So there were 79 muscles measured for the Mill River in 2015. In 2016, there was 51 muscles measured. more in 2015, and 11 for the Manhan River in 2015, and 72 for the Manhan River in 2016. The next number down is the sum of all the values. Then you have the mean. So the third one down is important. That's a useful measurement because that gives you the mean right there. Then you have the sum of squares. Then you have the variance, standard deviation, and standard error. So this third item is the mean, and the last item is the standard error. So the output gives you both those values, which is useful. And it gives you those values for each combination of your two factors, but it also gives the information for the factors pooled over the other factor. So row 1, remember, is the Mill River. So these values here is the Mill River for both years. So now we have, 79 plus 51 is 130. So this is for all the Mill River for both years. This is for all the Manhan River for both years. And then at the bottom of the column, these are your totals for each column. So this is all the mussels in 2015, that's the Mill and the Manhan River together. So 79 plus 11, you get 90. And these ones are all the mussels together for 2016. So 51 plus 72 is 123. So this includes the Manhan and the Mill River. And then this is the values for everything, all of the data, all totaled up together. So I've put all these values in a summary over here. I've just put them over here so you can see a little easier which one is the mean, etc. So these are these same cells, just labeled. I've got the Mill River in these two columns, and the Manhan River in these two columns. And then I've got the pooled data for the years and the pooled data for the location. So these 4 cells, the 2 by 2, is what's called your interaction. So that's your location by year interaction. So you've got each combination of those two factors, location and year. Then these ones here are what are called main effects, and these are the main effects for the year. So it's pooled across the location. So we have all the values for 2015, and here's all the values for 2016. So it's kind of ignoring location and just looking at year. So that's the main effect of year. And then over here is the main effect of location. And if we scroll down, you'll see this is what's called an ANOVA summary table down here. And it gives us the p-value for each of these different things. Now, unfortunately, it doesn't label them for you. So rows just says rows. Now, remember what we had in our rows was actually the location, right? So Mill River was the first row, right? Mill River was the first row, and the Manhan River was the second row. So rows is location, columns is year, and then row by column interaction is the year by location, or location by year interaction. The values that you need to report are the degrees of freedom of that particular thing that you're reporting, as well as the residual, or often called error, degrees of freedom for the whole model. So this is what we call the numerator, and this is the denominator of the degrees of freedom. And the way it's written is F sub 1, that's the first degrees of freedom, and then comma 2009, that's your residual or error degrees of freedom. And then you give the actual F value. So this row here is location. So we have F sub 1 comma 2009, and then I've given, oops, you can't see it, I've given the actual F value, which is 37.38. So that's our F value with our degrees of freedom, and that's how it's commonly given. You'll see that in pretty much every published paper. The F value and then the degrees of freedom are given as a subscript with a comma between them, numerator first, denominator second. And then you give the p-value. So the p-value for location is less, it's a very, very small number. It's less than 0.0001. So what does that mean? It means that location, because the value is less than 0.05, it means that it's highly significant. So we can say that there is a significant difference between these two locations. And since there's only two locations, we don't have to do any further testing. We know that there's a difference between the two locations that we have. And to know which one is greater, you just look at the means. And you can see that the mean for the mean muscle length at the Mill River is 61.7 millimeters if we round it up, and the mean for the Manhan is 45.2 millimeters. And so then we can say that the muscles at the Mill River are on average larger, significantly larger than the muscles at the Manhan River. For the columns, that's your year, our p-value is 0.0001, and here's the f value, 14.91. The degrees of freedom are the same, and again, this is significantly different. So we can, and the 2016 value in this case was greater, so we can say that the muscles on average were greater in bigger size, a larger length in 2016 than they were in 2015. And then the interaction term, you can see, is marginally not significant. So it's a little bit bigger than 0.05. Now, you do want to be careful in that if you have a significant interaction term, it's hard to actually interpret the main effects. So if you have a significant interaction term, you should just basically then focus on what that significant interaction actually is. If you do not have a significant interaction term, then you can focus more on the main effects. You'll notice, let's just pretend that we had a significant interaction term. It's actually pretty close to significant anyway. Now you'll notice that there's 4 different cells, 4 things to combine. So how do we know which ones are significantly different from the other ones? This value just says that there's some kind of significance going on in this interaction term, but it doesn't give you specifics about which ones are different from each other. To do that, you have to do a post-test, usually a Tukey, some kind of Tukey test. Here, the Vassar Stats gives the Tukey HSD test values. Unfortunately, the way they report the results here is a little bit tricky to interpret. But basically what it does is it tells you, let's just focus on the cells. This is for the interaction term, that the difference between the means, the absolute difference between any two means of the interaction terms, if the value that you get in the difference of the means is greater than 12.75, then you know that it's significantly different by at least a p of 0.05. So this is your critical value for the difference in means at a level of 0.05, p equals 0.05. So if the difference between your two means is actually greater than this, then you know it's at least significant at the 0.05 level. And this also shows the 0.01 level. So if it's greater than 15.47, then you know that it's more significant than a 0.01 level. So let's just give an example of how that would look. So all you have to do is take the means and subtract them. So let's just look at the Mill River between the 2 years. So we're just going to subtract those two values. And you want to do the absolute value between the values, so it doesn't matter which one's greater. So the absolute value for the difference between these two is 19.8817, rounded up to 19.9. 19.9 is greater than 12.75. It is also greater than 15.47. So you can say for that comparison that the p is less than 0.01. And so that's the Mill River between 2015 and 2016. Let's say we want to compare the Manhan between 2015 versus 2016. And here we're doing the Manhan. So now we're going to look at the difference between these two values. Now the difference is 6.94. 6.94 is not greater than 12.75. So in this case, we know that our P is greater than 0.05. So these two means are significantly different, but these two means are not. And you can do more comparisons. So you could do the Mill River in 2015 versus the Manhan in 2015, the Mill River in 2016 versus the Manhan River in 2016. You can do all the different pairwise comparisons that you're interested in, and then just compare them to these values. You can do the same for the main effects. You would just take the difference between the main effect means and see if that, so these are columns, so you look at the columns and see if the value is greater than these values. But in this case, we don't need to do that because we only have two categories. And when it says that, excuse me, the two categories are significantly different, we don't need to do further tests because we only have two categories. But if there were 3 years, you would want to do a post-test to see which of those 3 years are actually different from each other. So that's the gist of the actual test. Now that we have our statistical results, we also want to make sure we've graphed the data. Oftentimes, actually, I like to look at the graph before I do the test, the statistical test. It's not crucial what order you do it in necessarily, but it's useful to look at the graph when you're interpreting the results, because then you can just see, oh, the Mill River in 2016 was greater than 2015. We got that it was significant, but you know which one was bigger because you can just see it in the graph, so it's helpful. I've already rearranged the data to make it easier to graph over here. So I've just taken my means and standard errors. So you can see that I've just moved the mean for the Mill River in 2015 and 2016, and the Manhan in 2015, 2016, and also the standard errors, just the ones from the cells of the interaction terms over here. And even though our interaction term was marginally not significantly different, I'm going to show the data for the interaction in my graph. So I'm going to select my 2x2 little mean table here, and I'm going to go insert, and I'm going to pick a column graph or bar graph, if you prefer to call it. Excel calls it a column graph. And there's my graph. Now, this is not how I would like to view my graph. We need to get rid of the title. We need to, I would prefer, let's see, we'll move the legend to the top, or actually I usually prefer it to the top right. No, I want the top right. Top right. I like to get rid of, there's a line on the outside, the border, I usually get rid of that. So there's no line around this box. Get rid of these grid lines to make it a little cleaner. Add a solid line, kind of a medium gray. Change this one to medium gray. So now we have nice axes. We want to increase our font size quite a bit. Make that a little bigger. Let's add in our axis titles. So we need a label that describes both of the things, the labels shown on the axis. So in this case, it would be location. And our y-axis is our dependent variable. This is muscle length in millimeters. I usually like to make my labels stand out a little bit. We can add tick marks if you want to. Tick marks, major. Let's see, do we want outside or inside? Doesn't really matter. I'll do outside. There, that looks pretty good. And then we need to add our error bars. So let's start by clicking on the 2015 data. So you can see that both the blue bars are highlighted. I'm going to click on error bars. It puts in a default value of 1, which tells you nothing. So you need to click on more options and go to custom, specify value, get rid of these. And if I'm going too fast, you can always, go back over it over and over again. But also remember that I have a video showing you in much more detail how to make a bar graph, including error bars elsewhere. So I'm just going through this really quickly. So we're going to add the 2015 values, and then we're going to add the 2016 values. Custom, specify value, get rid of the ones. 2016. Make sure they look like they were matched up. So the biggest error bar we have is the Manhan in 2015, and that is the biggest bar. So it looks like they are good. I think we could make this go to 90 instead of 100. We don't want it at -10, we want it at 0. There, that looks pretty good. So there's our graph. And in your figure legend, you want to make sure to describe this graph really well. Make sure you describe what everything shown here is, that these values are means, plus or minus standard errors, what these things are, Mill River and Manhan River, that are found in, well, the Mill River location is in Northampton, Massachusetts. The Manhan River is actually in East Hampton, Massachusetts. When these values were taken, sampled, what kind of mussels are shown, all that kind of stuff. As well as you can report the statistics in the figure legend, or you could report them just in the text and say refer to text for statistical results. If we had a truly significant interaction term, you can do things like put different letters on the ones that are different. So let's say that these two values were the same. I'm trying to remember, is 20, if this one is significantly different from these two. I don't remember, but because I haven't done that value. But let's just say these two were not significantly different from each other. You could put a little A above each of those. Let's say this one was significantly greater than either of these, that could get a B, and then if this one was greater than this one, it could get a C. So you can just put different letters for ones that are significantly different, and put the same letter for ones that are not significantly different. And then in your figure legend, you would say that different letters were significantly different by a Tukey HSD test at a value of 0.05 or whatever the case may be. So that's the gist of how to actually perform a two-way ANOVA. And what I would say in terms of these actual results is that what this is telling us is that in general, the mussels in the Mill River are a little bit bigger, or significantly bigger than the Manhan River, and that in general, the mussels were larger in 2016, but a lot of that is really driven by this one value. And why the mussels are larger in the Mill River in 2016 isn't entirely clear, but at least it doesn't suggest at this point that there's any major negative effect from the redistribution of sediment, unless the reason for this bigger the mussels being bigger in the Mill River is because the small muscles got buried by sediment and suffocated. That could be a negative reaction. But it could also be that the increase in sediment and organic matter in the water gave the muscles more food, and they just grew faster, and that's how we got larger muscles. So the results of this can't tell us for sure how, we'd have to do further testing to understand exactly what's going on with these muscles. And that's an important aspect of using your statistics, is once you have your statistical results, trying to figure out what does it actually mean, what does it tell us, what can we say for sure, and what can we only guess at and have to do further testing to understand. Hopefully that gives you enough information on how to do a two-way ANOVA. But please ask if you need further help.